My dear friends, welcome to Rajshekar classes on applied data science with Python. This is lecture number 560. In this lecture, I will continue my discussion on RELUs. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 559. What is this? This is known as Leaky ReLU. What is this? This is parametric ReLU. What is parametric ReLU? In the case of parametric ReLU, your y equal to ax. In the case of leaky ReLU, your y equal to 0.01x. Means in the place of a, if I keep 0.01, I will get leaky ReLU. I can say leaky ReLU is a special case of parametric ReLU. We use a variant called Leaky ReLU. Leaky ReLU is very interesting idea. How does ReLU looks like? Just see this diagram. What is this? This is for ReLU. What is this? This is my Z and this one is ReLU of Z. ReLU has the problem. What is the problem in ReLU? Gradient, isn't it? What's the problem? ReLU has a problem. Gradient here is equal to 0. In the case of ReLU, what happens? This gradient at this part, your gradient is 0. Remember, at the end of the day, we will multiply lot of gradients. Let's not forget that what is your dou L by dou W11. We multiply lots of gradients because of chain rule. Now even one of them becomes 0. Let's ask ourselves, when do we have 0 gradient? Let's work it out and then come to leaky ReLU. What is when does this Z becomes negative, isn't it? Let's look at it. Let's take this. This is my Z. I can say this one is Z, isn't it? This is my if my Z is negative, then my f of z equal to 0. That point is important. When this f of z equals 0, if z is negative, then your f of z will be 0, isn't it? That's what ReLU says, isn't it? If f of z is 0, my derivative with respect to f of z will be 0. If f of z equals 0 means what? Derivative of f of z with respect to z will become 0. Means df by dz will be 0, isn't it? Derivative will be 0. If any derivative becomes 0, in chain rule, remember we multiply derivatives, isn't it? I can say in chain rule we multiply derivatives, isn't it? This could be, let me say, this could be this derivative could be 1, this derivative could be 1, and if this derivative is 0, means 0 into 1 into 1, the whole derivative becomes 0. That's actually a problem in ReLUs. Even if one of them are 0, the whole derivative becomes 0, which is a problem, because if the derivative becomes 0, what is our update function? Just try to recall our update function. If this derivative becomes 0, what happens? Wkij nu equal to Wkij volt minus eta into dou L by dou Wkij. If this derivative dou L by dou Wkij becomes 0, if this becomes 0, then your Wkij nu and your Wkij old are same, are same weight. The weights are not changing. If you see what happens, they are same. Weights are not changing. Whatever your learning rate, whatever happens, your Wkij nu is same as Wkij old, which means your weights are not changing anymore. When does this problem occurs? When z is negative. And when does z becomes negative? Imagine if all of your inputs, X is inputs here. For for all of your inputs for any neuron, let's assume all your inputs are normalized. Let me say, if your weights to the neuron are highly negative, because what is Z? Your Z is W transpose X. Given a neuron, you have X, which is input here, and you have the weights here, and just we are doing dot product between X and W. X is always normalized. We will come to that in one of the next videos. Just like your data normalization, which is a pre-processing step. But if your weights, all of them are negative, all of them are mostly negative. If your weights, all of them are mostly negative or large negative numbers, Z will become negative. If one Z becomes negative, your weights do not update anymore. Such a state is called deactivation state. When a neuron is in a dead activation state, which means if z is negative and f of z equal to 0, the derivative of f of z is also 0, isn't it? No. So whatever, whenever you have dead neuron, suppose you have model, suppose you have a model with, let me assume, suppose your derivative is 0, f of z equal to 0 means your derivative is 0. So whenever you have dead neuron, suppose you have a model with 20 activation, you have a model with 20 functions, 20 activation units. Let's say you have a model with 20 activation units across multiple layers. Let's assume 15 of them are 15 of let's assume 15 of them are dead. Let me assume in 20, 15 of them are dead. That's a terrible state, isn't it? That's a terrible state to be in, which means model is not learning anything because weights does not changing, because weights does not change much, isn't it? Because weights does not change much. Whenever you use ReLU, it is important to keep a count of how many activations become dead. If too many of your activations are become dead, what is dead means your Z that's going into a model becomes negative. If that happens, you need to debug and fix it. We will see how to fix some of the problems little later, but very simple fix for it is leaky ReLU. How does our ReLU looks like? Just see how does this ReLU looks like. If Z, if it has positive value and zero value. This is my ReLU. Just say this is my ReLU. This is what is this is my ReLU function. What is my Z here? This is my Z, isn't it? This is my Z, and what is this is my, I can say this is my f of Z. People said this part is very good. This part, which part is very good? People said this part is very good. No issue with this part. This part is very good, isn't it? Why can't we simply change? We have difficulty with this part, isn't it? We have difficulty with this 0. Why can't we simply change this? Just let me show this one. This part is good. We don't have any issue with this particular part, and we have an issue with this part. Why? Because your gradient becomes 0, means because of chain rule your derivative will become 0, isn't it? Why can't we simply change this, isn't it? Why can't we simply change this slightly? Instead of it becoming 0, what if I make it a different line, isn't it? Let me make it a different line. Just instead of this particular line, just I'm slightly moving this one. Instead of this direction, instead of straight line, just we are moving like this. This is leaky ReLU. Here you have straight line, but here just I'm taking little bit angle there. What if I make it different? I'm making a different line, isn't it? two different lines. This is, I have two different lines here. Just see, this is 45 degrees line. This is a line with some other degree, isn't it? I have two different lines. Two different lines. This is, of course, as I told you, this one is 45 degrees line. This is 45 degrees line. This is of course, we have angle here. This is different angle. Let me define the leaky ReLU. Leaky ReLU says that my f of x equal to x if x is greater than 0. F of x equal to 0.01x otherwise. Here we in starting in slide itself, we were saying that there is parametric ReLU f of x equal to ax. In the place of a, we are keeping 0.0, and we are giving a small value here. 0.01 is small value. This line, I can say, what is this line? This line is z. This line is z. This line is AZ. This one is Z. This one is AZ. What is here in the case of leaky ReLU? What is your A value? Your A value is 0.01, and the derivative is also just see. Let me check the derivative. What is straightforward? Your derivative d by dz of f leaky ReLU equal to 1 if z is positive, a if z is negative. A means in the case of parametric ReLU, in the place of 0.01 I am keeping a, therefore I am getting a here. A can be small value, a can be 0.01 in the case of leaky ReLU. With having small a here, you are avoiding the problem of dead activations, but you could run into a problem of vanishing gradient. But you are avoiding the problem of dead activation by keeping small value, but at the same time, you could run into the problem of vanishing gradient sometimes, isn't it? Because sometimes, not always, because your a here is small value between 0 and 1, and multiplying many of them when you have gradient which lies between 0 and 1, multiplying many of them again and again you can be into the problem of vanishing gradient. So typically people use ReLUs. So ReLUs do not have too much of problem with dead activation units. Sometimes it happens. So for most people, ReLU is the default choice. What is the potential problems here? Unbounded basically means as z increases, f of z also increases. There is no bond. It keeps increasing. But the biggest problem is dying ReLU. So dying ReLU problem or dying activation problem. Fix for it is leaky ReLU. So in a nutshell, to summarize ReLUs for you, ReLU have this big advantage. Is its speeds up convergence, convergence for you, isn't it? That's the major advantage. Next thing, it also speeds up because it is easy to compute. It is easy to compute f of z and derivative of f of z with respect to z. Both of them are easy because you don't have to compute exponential types of functions. But it has one major drawback, which is it could have dead ReLU units. So you need to be slightly aware of this dead activation unit. This happens sometimes if your weights are extremely large negative values. Only then you have the problem of dead activation units. When you have dead activation units, people simply use leaky ReLU or leaky ReLUs. I request all of you to go through this Wikipedia page. There are advantages, better gradient propagation, efficient computation, scalar invariant. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.